Hi, this is Jeff Spence, your Math 120 instructor, and this is our video lecture over section 4B titled The Power of Compounding. So in chapter 4, 4B, 4C, and 4D, we're going to look at various interest formulas and loan formulas, savings plans, things like that, how you can invest your money and how it will grow, or how you can pay off a loan and how the interest is created from those loans and how much you owe and things like that. So we're going to go from everything from just simple investments to savings plans where you budget out money, and we're going to look at loans like mortgages and car and or credit card loans at the end in 4D. So first we're going to start with the basics of the power of compounding. So um, we're going to invest what's called the principal. The principal in financial formulas is the balance upon which interest is paid. And the principal is our initial investment. Simple interest is the interest paid only on the original principal and not on any interest added at later dates. Sometimes bonds are like this. Not many things are like this anymore, but it still exists. Compound interest is the interest paid on both the original principal and on all interest that has been added to the original principal. And most accounts are like this, but the interest rates are so low you don't even really notice it's going on. So we're going to compare simple interest to compound interest for the first bit of this lesson. So it says, well, banks almost always pay compound interest. Bonds usually pay simple interest. Suppose you invest $1,000 in a savings bond that pays simple interest of 10% per year. How much total interest will you receive in 5 years? If the bond paid compound interest, would you receive more or less total interest? Explain. So we're going to compare the 1,000 invested at 10% in simple interest in 5 years and the 1,000 invested in compound interest at 10% for 5 years. So the only difference will be simple versus compound interest. So simple interest, it says every year you receive the same interest payment, which is 10% of the $1,000. So 10% of 1,000 is 100. So every year you're going to get, for the 5 years, you're going to get $100. So therefore you receive a total of 500 interest over the 5 years. So that should make sense. With compound interest, you receive more than 500 in interest because the interest each year is calculated on your growing balance rather than your original investment. So let's look at that. So the first interest payment, well, this should actually really, it's the second interest payment, excuse me. So the first interest payment is still the 10% of 1,000, which is 100. The second interest payment, excuse me, is 10% of that 1,100 because you got 100 in interest the first year, and then we're taking 10% of that now 1,100, which is 110. So notice 110 in the second year is more than the 100 that we're getting from the simple interest. Second, actually the third interest payment will be 10% of now 1,210 because I add this 110 onto the 1,100, and now I take the interest of that growing account, and it's $121. So you can see that the interest each year is growing, and it's a lot more than $100 each year. So this raises your balance faster than simple interest. So compounding interest is better. So here's our formula. If we pay interest once a year, okay, and let's say we invest $100 and counts 2 years. So we're just going to compare this now. This is $100, and it'll be really easy to see the percent interest. Once again, one is 10% per year simple interest, and one is 10% per year compound interest over a 5-year period. And we'll make a table to show these growing accounts. So here's the account on the left, simple interest. What they do is they take 10% of the principal, which is $100, that's $10. So we add $10 each time. You can see it going up by 10 each time. Alright, but with compound interest, notice we have the $10. You add the $10 on, you have 110. So the 10% is taken not of 100, but of the growing amount, the 110. This 10% is $11. You add $11 on, you're at 121. 10% of 121, 1210. Add that on, and now you're at 133.10, and so on and so forth until we get down to the end of the 5th year, and we have now $161.05 versus $150. So the power of compounding. All right, so we're just going to check this last number, 161.05, using the formula right here, okay? So principal is going to be 100 times 1 plus the APR, which is 10%, so 0.10, times 5 years, or sorry, to the 5th year. So we'll plug it into the formula. There's our formula, $100 times 1 plus 10% is 0.10 to the fifth year. And we get 161.05, which is exactly what showed up in the table at the end of the 5th year. So now we have a formula. Instead of having to do a table to go year by year and iterate the interest each year, we have a formula that can jump ahead to the end of a number of year period, which is really nice. Okay. Sometimes banks pay interest compounded more than 1 times a year, so they might say biannually, which means twice a year. They might say quarterly, which means 4 times a year. They might say monthly, which is 12 times a year, or daily, which is 365 times a year. So now we have this new element n. Okay, that's the new element here, the number of compounding periods per year. And so we divide the APR by that because we're going to pay out that many times. But we also take that times the number of years because that'll tell us the total number of payments. So over 5 years, if you have quarterly payments, that's 4 times 5. They're going to do 20 interest compoundings on your money if they did quarterly over 5 years. So let's say we deposit $5,000 in a bank that pays APR of 3% and compounds interest monthly. So that means N will be 12 here, monthly. How much money will you have after 5 years? Compare this to the amount you've had if interest were only paid once a year. So we'll do both formulas. So the starting principal is 5,000. The interest is 0.03. Remember, you got to convert these percents into a decimal. Monthly compounding means that interest is paid 12 times a year, so n equals 12, and we're compounding over a period of 5 years. So let's follow the formula. Here's our formula now. And the big thing I would say is when you do your exponent, make sure to figure out this number off to the side because I don't think we're going to remember it all the time to put parentheses here. So they'll show it in the next step. Notice that they did the 12 times 5 as 60, and then they'll raise it to the 60th instead of raising it to the 12 times 5 in parentheses. So 5,000 times 1 plus 0.0025 to the 60th because it's 5808 if we compounded monthly over 5 years, 5808. But if we followed the basic interest formula, compound interest formula, once a year, then we would have this formula, 5,000 times 1 plus 0.03 to the 5th, 57.96. We can see a difference in about a little more than $10. Okay, so after 5 years, monthly compounding gives you a balance of 5808, while annual compounding gives you a balance of 57.96.37. That's a difference in $11.71, even though the APR is the same in both cases. So the big lesson here is that the more compounding you get, the more interest you're going to receive. Compounding is more like an exponential growth. It's slow at the beginning and it'll eventually go fast, but more compounding means more interest. Now, when you're saving, that's good, but when you have a credit card loan or something like that, which is compounded every month, that's not necessarily good. So I will say more compounding means more interest, but sometimes you owe interest, like in loans, which we'll see in the future. But right now, more compounding means more interest, which is good when you're saving. All right, second to last thing is the annual percentage yield, also called the effective yield or simply the yield, is the annual percentage by which a balance increases in 1 year. It is equal to the APR if the interest is compounded annually, once a year. But if we compound more than once a year, we notice the difference in interest here. So it is greater than the APR if interest is compounded more than once a year. So APR versus APY. APR is the quoted rate by the bank. The APY is actually what you're going to get if there's more than one compounding per year. And that's what we're saying here. Okay, so show how different compounding periods affect the APY for an APR of 8%. So annual percentage yield for APR with 8% with various numbers of compounding periods shows that if we have one compounding per year, then 8% is still 8%. But if we have 4 compoundings per year, if we iterate the 8% 4 times, it'll become 8.23421, etc. percent. And notice as we get up to a billion compoundings per year, it gets up to about 8.3. But notice the change isn't that significant once we get past 365 days. It's all 8.32, 8.32, 8.32. So that's what they're showing there. As the number of compoundings per year increases, the APY gets closer and closer to the APY for continuous compounding. Compound interest formula for continuous compounding. This is not really real in the financial world, but it can happen in certain instances in chemistry and physics and things like that we'll use this formula. The amount is the principal times the exponential growth factor, which is E, to the APR times Y. So let's say we deposit 100 in an account with the APR of 8% in continuous compounding. How much will you have after 8 years? You just have to know, since it says continuous compounding, that we're looking at the formula E, with E in it, excuse me. So we plug in our numbers. Principal is $100, APR is 0.08. We take 100 times E to the 0.08 times 10 and get $222.50. So in 10 years, if it continuously compounds, it'll more than double. So good luck using these formulas. A big part of this unit is actually getting comfortable with your calculator and typing these numbers into your formula. The actual problems aren't that difficult, reading and understanding which formula to use. Make sure you practice your calculator. Don't be using cell phone calculators for this unit. Start getting a real calculator, and I'll mention that again in D2L. And good luck.